Okay, so good afternoon all. Welcome to session 7 on principles of extractive metallurgy. Right, so in previous few lectures we have discussed about mostly about the Lingam diagrams and the thermodynamic diagrams, right? So we have discussed even about the metal sulfur oxygen phase diagram, so different types of phase diagrams, and also how the Gibbs phrase rule and degrees of freedom will affect your overall the components, right? So whatever you are taking. So for now we will start discussing on, in this session we will start mostly discuss on smelting and bits and pieces about slags, and then we finally go to the problem solving session. Okay, we will solve few problems, right? So let's start with the smelting. I have explained before the difference between smelting and melting. So melting is your direct conversion, is a physical process. So melting is my physical process which converts my solid to liquid, right? So that's what we normally see, or that's what we normally hear, right? So we normally hear melting. So no one says melting, right? So melting is physical process in which you directly convert solid to liquid. Now smelting, whereas may involve few chemical reactions. Okay, so it is also a conversion process. So it is a part of pyrometallurgical process. So why? Because we are supplying heat energy. Right. So it is a unit process. So not unit operation. Unit operations are like mostly before whatever you do, combination, post rotation, or the few types of enrichment process that you do, right? That is the unit operation. Now we are talking about unit process. So yeah, again the same. You do the heating process. So you will get a melt. So you form a melting process, and in this you start with ore. Right, you start with an ore which contains your metal and impurities. Then you heat, right? You heat it, and also you add flux, and there will be a reaction between the flux and impurities, and you will have your metal and slag. This is the most basic operation, right? So if you are talking about only basic operations, then these are the different. These you will end up slag and metal, right? And what happens slag where impurities and flux will react to form slag. So we'll discuss about slag in detail in the next few slides. Yeah, and depending upon this, let's say my ore is a sulfide ore, and my metal. If my metal gets separate out from my sulfide ore, then that is called as a matte smelting. And if I have ore and also I add reducing agents, right? So plus carbon and some flux is added. So my slag, I will get a slag and then my metal, liquid metal, right? So both are in liquid state. This is called as a reduction smelting. So in smelting you basically involve extra chemical process. Okay, so that's why we give a name called smelting, because in melting you directly have a complete liquid, there is no immiscibility, but in this you will have a different liquids, right? So you will have your slag and also you will have your metal, liquid metal, right? So this is about matte smelting, reduction smelting, and the other one is called as a flash smelting. Now what is flash smelting? Just like the name suggests, it happens at a very fast intervals. Okay? So it won't take much time as the other smelting process like matte and reduction smelting. So it happens within a few seconds, So in flash smelting, it's like you disperse the powder and you burst air or oxidizing elements, whatever you are trying to do, from bottom to top, and from top to bottom you are suspending your particles. Okay, so because of the high surface area, right, because you are like dispersing, right, you are mostly dispersing your powder particles in a shaft. If I take, it is a big vertical furnace which is heated up, so we can call it as a shaft, and you throw the powder from top, so it gets dispersed, it gets sprinkled on most of the side. So then you purge oxidizing or reducing air from bottom. So because of this, the powder particles can freely move, so and the air can pass through, and because of this high surface area, it will happen very fast. So that's why we call it as a flash smelting. Now let's move on to the matte smelting. Now matte smelting is nothing but your mixture of sulfides, right? So slag is nothing but the mixture of oxides, and there might be some minute amount of sulfides, selenides, silicates. So matte is mostly sulfides. Okay, so we call matte because of if it is a mixture of sulfides, then we call it as a matte. And we mostly see this in whatever copper, right? Chalcopyrite. When you are dealing with chalcopyrite, you will end up with Cu2s and Fe(S), right? So you will have a mixture of sulfides when you do the melting. That is called a matte smelting. Now, when you do the melting of this sulfide ore, and then you add some flux in it, so flux will react with impurities, and then it will form your matte. These are sulfides, okay? So sulfides. So you add flux, right? So that's what is happening. You have sulfides, then you add some flux to catch the impurities, right? So and then you supply whether some heat or oxidizing or reducing agents, depending upon what you are trying to do. You will end up with matte plus slag plus gases. Right? Now we know in copper extraction we normally use chalcopyrite ore. So chalcopyrite is nothing but CuFeS2, right? So this is the chalcopyrite, and then also Fe(S2). If we are talking about Cu2s, then it should be Fe(S), right? Okay. So what we do is, if we are talking about chalcopyrite, if we are talking about the copper extraction, we first initially, please remember this. So initially you have your chalcopyrite and sulfide ores. So what we are trying to do is, we are trying to remove this sulfur. So that is our main goal. Now the thing is, if you want to remove the sulfur, how you are going to do? We cannot use the reducing agents like carbon or hydrogen. We have seen that, right? The Gibbs free energy doesn't make you do it. So then it will be highly energy intensive also. So we cannot use the reducing agents. So what we can do? We can convert them into oxides. So that is one way. If you convert them into oxides, then you know what to do, right? Oxides can be reduced. So you want to try to convert them into oxides. So that's what we are trying to do. And we also want to pick up them. So conventional slags we have seen can easily pick up oxides, right? So that's what we are trying to do. We are trying to partially roast this guy. Okay, so it's not like we are doing the complete roasting, we are partially roasting. And why we are doing it? So whenever you try to do, you have your Cu2s. So yeah, iron is more susceptible for oxidizing when compared to your copper sulfide. So that's why iron will oxidize first. So iron will take all the oxygen that's remaining, that is there. So it will convert into your oxide. Okay. Let's say you even form Fe2O3, there might be form of Fe3O4. Some copper sulfide will also convert into copper oxide. That might also will happen, right? You cannot say that won't happen. That might also will happen. And depending upon the partial pressure of oxygen, you can end up with two products. Either you can have oxygen, see copper oxide, or you can have copper sulfide. Now, what is the difference? See, whenever you have excess amount of oxygen, you will end up with copper oxide. If you have less amount of oxygen than the required, then you will end up with Cu2O. Right? For every 2 copper atoms, you will have 1 oxygen atom. And if you have excess, you will end up with copper oxide. For like stoichiometric, for every copper, you will have 1 oxygen atom. Now, once I do this, then what I'm going to do, I'm going to melt it. Right? And melting, what I'm going to do? I'm going to add flux and I'm going to heat it. So what's going to happen is, so whatever the oxides are there, and because I'm adding silica, right? So because they are basic oxides, right? Whatever we are forming, they are basic oxides. FeO is your basic oxide. Now what this silica do? Silica is your acidic oxide. So this acidic oxide will pick up your FeO, Cu2 and some other oxides. See, these are very difficult to melt because they have very high melting point when compared to FeO reacting with silica. So that's why these will get reduced. Okay. Now we'll come to this guy. So initially this FeO will be picked up by your silica, and then you will have FeSiO3, which is your silicate, iron silicate. Okay, there can be other type of silicates also. Let's not discuss go deep into it. So this will form your slag, and then you have your matte. Right, so that's what going to happen. Now if you oxidize, if you do the dead roasting, I mean if you roast everything, yeah, there is this term called dead roasting. Dead roasting is nothing but you roast everything, right? There is no any type of sulfides, nitrites, anything is there. You will form, your end product will be complete oxides. Okay, so full oxidation, not like half oxidation, just like in copper oxide. It will not from cuprous oxide, it will directly from copper oxide, CuO. So it's like complete roasting. You are giving excess amount of oxygen such that everything will convert into their stable oxide forms. Okay, so that is called as a dead roasting. Now if you do the dead roasting, then you will end up with copper oxide. So our slag is also there. So our slag, what it does is, it will pick up your copper oxide. So that's why you only do partial roasting. Okay, so that's why we will not use, we will not completely convert everything into our oxides. Okay, so that's why we do partial roasting, and also whatever the sulfide that is left, that can react with your copper oxide to give you pure copper and SO2. This is also a very important reaction that happens during your conversion process. Whatever the copper sulfide that you have left during a matte, so once you do the matte, once you smelt everything, you will separate the slag. So slag contains mostly your FeO. Some amount of copper oxide will be there, because see, you cannot control very precisely, because even though iron has more susceptible to oxidation, there will be some area where copper oxide will be rich, so this copper oxide will get also oxidized. So you cannot control, iron oxide will only get oxidized, copper. There are ways in which you can do it, but industries, they mostly don't prefer, because again it will increase your uh, your process parameters and also the different things will come into picture. There is a term called the selective oxidation, where you just selectively oxidize one element and you keep other element as it is. So that can be done, but in industrial processes mostly they do not use those things, because again it will involve so many things, right? So you need to maintain this amount of partial pressures of something such that this will get oxidized and that will not. In lab scale it is okay, because the system is very small. So in industry the system is very large, right? You deal in tons, not in grams, milligrams, right? In lab it is okay, we deal with grams and milligrams. So again the system chamber is very small, but in industries that is not the case. Now in refining, after the let's not go to the jump very to the last point. So after matte you do the converting process, where you convert this sulfides into oxides by purging oxygen. So this some copper oxide will be formed, and that copper oxide will again react with your copper sulfide. It will convert into copper. Okay, and there is also this reaction where if you do the partial oxidation, that is partial roasting, there might be some FES also will be remaining, right? Some FES will also be remaining, and that FES will react with your copper oxide, whatever the copper oxide was there that has been converted, and it will form FeO plus Cu2s. Again, this is also very important reaction, because this unconverted, the partial roasting, whatever you are trying to do, will make sure that whatever the remained iron sulfide will react with whatever the over oxidized copper oxide or copper sulfide will displace that sulfur, and it will take oxygen from copper and it will give sulfur to the copper. Okay, so that's how you have a copper sulfide, and this again copper sulfide will not go into slag, it will come out. So this is one important point. So that's why we do the partial roasting, not the dead roasting. You can even ask why not completely melt, right? So why not just, instead of going partial roasting, why not you do the whole smelting of sulfides? Yeah, you can do that, but once you do that, you will only end up with matte, right? You will not have any slag. That means you need to burn more amount of energy, because now the system is very large, right? So you need to, first thing is that you need to burn more amount of energy, and that will stress when you go to converting process. Okay, there you need to even oxidize iron also, so that the iron will get picked up. But you need to, so once you have your melt, now you are trying to purge oxygen such that this, whatever the iron sulfide is there, that need to convert it. So instead of stressing everything on converting, so yeah, I will do it. So let's say okay, so instead of saying it in air, let me draw this. So this is my partial roasting, right? And then we move on to the smelting. So far so good. And then we will go to converting. See, initially there will be some froth flotation, because we are dealing sulfide ores, there will be froth flotation or combination. So we are not going to discuss about that, because we already know what's going to happen there. And then we will do the refining. If I am talking about low grade sulfide ores, right? If I am talking about low grade sulfide ores, not oxide ores, okay? Sulfide ore of copper. So we know what happens in partial roasting. We convert some of Fe to FeO and some of CuS to Cu. It will happen Cu2O. So if we do not do this process, we directly go to smelting. We have matte. It contains FeS and Cu2s. Then we go for converting process. In converting process, what you do, you also, there might be some supply of heat, because okay, we will discuss that, and then you separate oxygen. Now in converting, what you do is you convert whatever the copper sulfide is there into copper oxide. So that's what we are trying to do, and that copper, some of the copper sulfide that has been left, that will again react with, and it will form copper. Right? So this is what happens, and whatever the iron sulfide that has been remained, that will also react with your copper oxide. It will give Cu2s plus SO2. Now, so if we do not do the partial roasting, then the whole thing will be stressed on converting process, right? So everything must be happening in one process. Again, that is not feasible because there is a lot amount of energy is involved, because you need to melt large amounts, and because copper sulfide and iron sulfide are there as it is, you need to melt more. So if it is iron oxide, then slag has a very low melting point. You do not need to go that much high amount of energy. So again, that is one case. So again, you are stressing more amount of your process and converting process, which is not feasible. And finally, you will have refining. This will not change because once the converting happens, refining you will have 99% blister copper. Then you do the refining. Okay. So then here you will have a large amount of slag that has been created, right? Because you are not doing anything in smelting. You are not separating slag in smelting process. So a very large amount of slag has been created here. So again, that is not a good thing, because a large amount of slag needs handling, and also more amount of pickup will be also there with the copper oxide. So whenever you are supplying oxygen, there will be a copper also will be converted, right, into oxide. So that also will be again picked up. So again, that is not needed, right? That is not viable. So more amount of copper will be lost. So yeah, so that's why we do the partial roasting in copper extraction process. Right. Now coming back to we have discussed a lot, lots of copper smelting, right? So now what are different types of molten layers that can be formed? I mean the immiscible molten layers. So let's take lead as an example. You have lead sulfides. So if you are talking about lead bullion, right? So whenever we are talking about lead extraction, there will be your lead sulfide ores. So what we do, we first convert them into sulfides, right, oxides. Then we reduce with your carbon to get lead. Okay. So there are so many layers that has been formed because the lead sulfide ores of lead has so many impurities. You will have so many layers also, right? So the first layer will be your silicate. So then you will have matte, that means sulfides. So whatever the oxides are there, they will react with your silica and they will form silicates, right? So this is your first layer. And in here you will have calcium, silicon. Obviously calcium will be there, silicon, aluminum will be there, magnesium will be there, zinc will be there, and iron. Because they are the basic oxides that will react with your acidic oxide silica and will form silicate. And then you have matte, the sulfides, mostly your copper and some part of iron. Then you will have species. So that is arsenides. Arsenide layer, not a species. So name itself suggests I have arsenide, and then your antimony and some part of iron, and finally you will have metal, that means the lead bullion. Okay. So this is called slag, this is called as matte, this is called speech, and this is called as bullion. Normal lengths. Okay. Not scientific names, they're normal lengths. Okay. So what is happening? So density will go on increasing when you move from top to bottom. So lead has a higher density when compared to speech. So and then you will have matte, and then you have slag. So slag has the lowest density. Okay. So this is what happens in lead extraction. Now we need to know what is flux. So flux is nothing but mostly we use some additives. What it does is it will react with your impurities. So main function of your flux is to form slag. So it will react with impurities and it will form slag. Okay. So that is the main function of flux. And what are the different types of flux you see? So depending upon your type of depending on what type of impurities there are. So what is the type of slag that you are trying to form? So it will depend upon that. So in your compounds, so for example, if I have a silica, which happens in iron ores, and then if you want to remove this silica, you add calcium oxide. So calcium oxide will react with silica, it will form CaSiO. and it will form more different number of silicates depending upon how the silica is present. Okay. So depending upon the basicity, you can have different types of silicates. Okay. So if it is less basic, if it is neutral, then you will have this calcium silicate, and if it is acidic, then it will have different types of silicate. If you have basic, then again the same calcium silicate itself you will have. So yeah, and another thing of flux is it will reduce your melting point. Okay, so it will form a eutectic point. So what does eutectic mean? Eutectic is nothing but, in metallurgical sense, eutectic is nothing but, suppose you have a one phase of A and another phase of B. So it has melting point of so this guy's melting point is this, and this guy's melting point is this. So it is TA and it is TB. Okay, these two guys have melting points, TA and TB. Now what I am trying to do, I am trying to melt them. So when I am trying to melt them by combining, okay, I combine them and trying to melt. So what happens is, when at a certain composition of A is to B, let's draw good. So So what we are seeing is this point. So at some proportions of A is to B, their melting point is much less when compared to their initial phases, right? Let's say TA has 1500 degrees centigrade, TB has 1400 degrees centigrade, then TE, the eutectic point, has a 1200 degrees centigrade. So it will decrease your melting temperature. So again, that is one good advantage of the flux, reacting with silicates, reacting with impurities to form slags, and they have very much less temperature when compared to your initial phases. Okay, so that is about flux. Now coming to the reduction smelting. So we have seen the matte smelting, right? So coming to the reduction smelting. So in reduction smelting, right, the name itself suggests you have your reduction metal oxide will convert into metal, and your melting smelting, sorry. So smelting, you will have your gangue being converted into slag. Right? So chemical reactions sure happens. So that's the only difference between your smelting and melting. You will involve some chemical reactions, and also you need not to go to the temperatures where you do at melting. Okay? So that's the only difference. Now these two processes happens at a time, so that's why we call it as a reduction smelting. So reduction smelting mostly happens, the best example for reduction smelting is reduction of Fe2O3 to Fe, which happens in the most famous shaft we use is the blast furnace. So why blast? Because you have your air coming from tuyeres. Tuyeres are nothing but the straws indirectly, or most common way to say. So they just blow air from bottom, and you are charging your ore from the top. So that's a counter current. You are blasting and that is charging. So that's the both happens. The reduction also will happen, and also your smelting also will happen. So both of these things will happen, and same goes for lead, and the same happens in zinc also. Okay, but the zinc furnace, or rather the blast furnace for zinc reduction when we use, there is this zinc. So there are different types of outputs, right? So one of the output is gas, right? So you can call it as a zinc dust. So This is, let's suppose this is my blast furnace. Okay, I'm only drawing the half of it. So here it is charging. Yeah, so then you will have your zinc dust coming out. So in that zinc dust it may contain lots amount of iron oxide also. So again that can be recycled too. So that is the other part. Now what we do is we take lump metal oxide ore, or you make concentrates, or you make pellets or sinters, depending upon what you are trying to do, and are smelted under your highly reducing conditions, with some of your reducing agents, and then you also add flux, so impurities react to form slag. So that's what happened. And the reducing agents can be carbon. That means carbon will be oxidized to CO2, and because the carbon dioxide is not stable at the temperature, so it will again react with C, it will give you carbon monoxide. Okay, so this thing normally happens. So carbon dioxide is very good reducing agent, so it will reduce your oxides and form carbon dioxide. So, and you can even add hydrogen also. So it depends on what you are trying to do. Okay, so yeah. Now moving on to different types of reducing agents. So see, reducing. So one good thing about reduction with carbon is carbon can take load, right? The coke can take load. So that's why your blast furnace is very tall, right? So whatever the coke is there, that can take the load. It will not break that easily. So that's why when reduction with carbon, even if you go the high temperatures, it always requires high temperatures, because whenever you try to oxidize carbon, it will form carbon dioxide, and to maintain the carbon dioxide conversion to carbon monoxide, you need to maintain high temperatures. So that is one drawback. But the next good thing is it can take the load, bear your load. And sometimes some metals may form carbides also when they react with carbon. So again, that is not good. So yeah, and you can use some metals also to reduce iron. So the best one is thermite process, used in railways, right? So you take iron powder and then you mix it with aluminum and you do the ignition. So once you ignite, aluminum will just take out the oxygen, it will form Al2O3 and it will give you pure iron. So this is highly exothermic reaction. Okay, all you need to do is supply a single spark and reaction will carry out. So at top you will left with alumina, and the bottom you will left with your iron. Okay, so directly metals also can be used to reduce. So that is called as a metallothermic process. Okay, so yeah, now that's all about smelting. Now let's move on to the slags. Okay, so metallurgical slags, or should I say? Now what happens in metallurgical slags? Right, so what is slag? Again, it is just a mixture of oxides. Some sulfides also will be there, but there will be in a minor quantities. The major component of slag is your oxides. Okay. Now, slag is lighter than your metal. We have seen that, right? So in lead reduction or lead extraction, right? So what are the different properties of slag? Slag is very much important in your metal refining or metal production. Okay. Now let's talk about refining. In metal production, the slag is the most important thing, because slag has many distinct properties. One, it will pick up impurities. Okay. Two, it will make sure if some of your oxides or some of your metal, if picked up in your slag, if you add something, that can be reduced. Okay, so metal pickup metal pickup and release. This is also very important. Okay, so which can be avoided. And then next thing is it acts as a thermal barrier. And because it is covering your metal, right? And slags are mostly oxides. So oxides do not have good thermal conductivity, so they are not metals, right? So that's why they can act as a thermal barrier. And yeah, to maintain the composition of your melt, right? So different things which the slag can be used for. Okay, so yeah, so slag can be even used as a thing, and also it can be used as a reservoir for chemical reactants, right? So suppose if you want to add something, then this slag can act as a reservoir for it. So chemical elements reservoir, or I can just call it as chemical reservoir. So these are the different properties slag can be used for. Okay, now let's move on to slag properties, right? So we know what are the components and functions. Now let's move on to the structure. See, as we know, slags are mostly made up of oxides. Then what are those oxides? Right. So we have seen acidic and basic oxides, right? Now, so for slags to form, you need to form bonding, right? Bonding also is very important. So how this bonding happens is it happens via coordination, right? And coordination depends upon the size of your cation and anion, right? So again, so if I am talking about cation and anion, they can form ionic bond, and also they can form cation, covalent bond. So you also if I am talking about cation and anion, then also I am talking about the charge, right? Charge is important. The size is also important. What is the size of cation? What is the size of anion? Okay. Now, if I have a big charge on my element, then my covalent character will increase. Why? Because there will be a lot of electrostatic attractions between cation and your anion. So if I have small charge, then my ionic nature will increase. So whatever the compound you take, it cannot have 100% ionic or 100% covalent. It contains some percent of ionic nature and some percent of covalent nature. Maybe like 92% of ionic. So still you will find some covalent nature or some ionic nature residual in your bonding. Okay, so yeah, and whoever has a covalent nature, they are very hard to break. That means they have very high melting points. And whichever has ionic, they have low melting points. They can be easily dissociated also, so they can easily ionized. They cannot be ionized. They cannot be braked. Okay, so that is also again one thing, right? And the coordination number, right? So it is again simple. So coordination, what does coordination says, right? So let's say for example, my cation RC by RA, that means the radius of cation divided by radius of anion, right? If my radius of cation is large when compared to the radius of anion, then I will be surrounded by more number of oxygen atoms, right? So So what the cation tries in a crystal or a unit lattice, it tries to get surrounded by as many number of anions as possible, right? So if my cation size is big, I can accommodate more number of anions around it, right? So that's why the if my RC by RA ratio is, let's say, 0.732 to 0.414, I will have more number of anions surrounding my cation, right? So that's what happens. So whenever I have calcium oxide, manganese oxide, iron oxide, they have RC by RA ratios lying between 0.7 to 0.4. So they have whatever coordination, 6. Coordination number is 6, and if something has 6 atoms being surrounded, then you can call it as an octahedron or octahedral wide. Octahedral, not octahedral wide. So the empty space that has been formed when some octahedral shaped atoms come together, not octahedral shaped atoms, if atoms arrange themselves in shape of an octahedra, then the empty space in that octahedra is called as octahedral, right? And the best way to represent is let's say if I have an atom, there is another atom, and there is another atom, and this empty space, if I put let's say another atom here, okay? So now if I try to put another atom here, another atom here, another atom, okay? So then it will form octahedron. So if I try to show it, then it will mostly look like this. It doesn't look good. So I will try to, let me draw the diagram. So this is your first layer, and your second layer will come like this. Okay, and in between you have your void. So that space is called as an octahedral void. So that is the other case. Let's not talk about that. So this is how they get surrounded. Now if my so you can see these are all basic oxides, right? Now, and the next one is, let's say if I'm talking about Al2O3, TiO2, SiO2, phosphorus pentoxide, P2O5, and if my RC by RA lies between 0.414 to 0.225, then that is called as a tetrahedral. You can see most of them are acidic oxides except Al2O3, which is an amphoteric. Okay, so you can see that there will be acidic oxides. Now, how the name basic and acidic oxides came from? It's not like we are dealing with pH, right? It's not like silica will decrease your pH value or calcium oxide will increase. Even though it will form a buffer solution, it will increase pH. They will not increase or decrease pH. The main reason that comes from is there is this another definition for oxidizing and reducing agents, right? If someone gives you oxygen atom, that is called as oxidizing. If someone takes out oxygen, that is called as a reducing. The same goes here. Calcium gives out oxygen, so that's why it's called as a basic oxide. And silica will take oxygen, that's why it is called as an acidic oxide. So that is one way, another way of saying acidic and basic. Okay, so if you are talking about silica, right? So silica will form a tetrahedron. Okay, so right now it's thick lines because they are appearing, right? these, they do not form bonds. So let's not write like this. Okay? Instead of this, there is one atom, this is another atom, this is another atom, and my silicon will be in red in color. Okay, this is my silicon. So this oxygen will have a bond, this will have a bond like this guy will have like this, and this guy will have a bond like this. Okay, now the tetrahedra, how this tetrahedra looks like. So that's why we call it as a tetrahedra. Even though the external diagram looks like a tetrahedra, not the bonds. Okay, so silica will form 4 bonds, so that's how it forms, and this oxygen will be again linked to a different silicon atom. Again this guy, some other here, and this guy also will, this oxygen atom will also bond this guy, this guy, this guy, and this guy. So that's how they will form a 3-dimensional structure. And each oxygen atom sitting at the tetrahedral corner will form 2 bonds with the different silicon atoms. Okay, so that's how they will form a different 3-dimensional structure. Now what this calcium oxide does, this calcium oxide will give away its oxygen atom, right? So you will have your oxygen, and this oxygen will be given to one of the silicon atoms, because when you try to break this, one silicon atom will get oxygen, the other will not get the oxygen atom. So what this excess oxygen, the free oxygen, is going to do, it will get associated with that extra silicon atom, that silicon atom which we have cut right now, which is deficient in silica. So that's how you will have different silicate chains. You will have SiO4 13 minus 10, and then you can have Si3O10 minus 8, and then you can have SiO4 okay, SiO4 minus 4. So at first you will have silica, right? Now you add oxygen, some silicon atoms will go away, some silicon will break. So that's how some silicon atoms will come out. Okay, they will not be in a chain anymore or 3-dimensional structure. Again you add more amount of, see, now I am trying to add calcium oxide. Okay, that means oxygen is being added, so silica is getting away, right? So you will have free silicon, not silicon, so SiO4 will have some free silicon. And if I add more amount of calcium oxide, again the bonds will be broken. Again you will have some more silica coming out, and finally you add enough amount of calcium oxide, that means enough amount of oxygen atoms, you will only have silica, SiO4 minus tetrahedra. Okay, there is a complete breakage of chains. There will be no 3-dimensional structure anymore. So that's what happens when you add calcium oxide. Now coming to the properties. And when you talk about properties, you will have both physical and chemical properties. Okay, let's go on to your chemical properties. The first thing is the basicity. What do you mean by basicity? Basicity is nothing but what is the power of your oxygen donation, right? So in slags, when a basic oxide generates O minus 2, and this when acid oxides come into picture, they will capture this O minus 2 and they will form their respective, the chain will be broken, right? So now when you add enough amount of calcium oxide such that everything will get converted into, you will only find this type of silica. Okay, You will not find any type of silicates. At Si3, Si4, no. Complex silicates, you will not find this type of complex silicates. That means the complete breakage of chains will happen. And this slag is called as a neutral slag. Why? Because you are not, you are totally breaking the chain. Right? So whatever the oxygen is there being absorbed by silica, SiO2. So that's why you will have a neutral slag. Now, the other thing is, so how many calcium oxide should be, how many moles of calcium oxide should be given such that you will have only SiO4 minus 1, right? That is also one question. So now we know SiO will form a 3-dimensional structure, right? That thing you know. Now initially I have SiO2, so to completely break everything, the chain breakage, you will finally form So when we move on to the last part, what are we remind with? SiO4 minus 4, right? Yeah, SiO4 minus 4. That is what we are reminded with, right? SiO4 minus 4. So how many oxygens I need required to finally get this structure? 2 oxygen ions, right? So that's how I will form this guy. And to form this guy, 2 moles of two number of oxygen ions are required, and to get 2 number of oxygen ions, I need to supply 2 moles of calcium oxide. So for every 1 mole of silica, I need to supply 2 moles of calcium oxide. So if my slag contains, let's say this is my total slag, then what is my silica concentration? If my silica concentration in my slag is 33.3%, by combining, when I am talking about calcium oxide which is remaining, then my slag is called as a neutral slag. Right? And why is that? Because whenever you see, when I am talking about silica, so I have one oxygen atom, I have another oxygen atom, another oxygen atom. So the effective number of silicon atoms. So each, let's see, another silicon. Now if I'm talking about the effective number of silica, right? This is actually this should be my chain. Right? So if I'm talking about effective number of silica atoms, so I should say, if I'm talking about only one chain, let's say I'm talking about this whole chain, then each oxygen is shared by 2 silicon atoms. But here the silicon atom is not being shared, right? In this structure there is only one silicon atom, so I have one silicon atom, right? And the next thing is, there are 4 oxygen atoms. Not all oxygen atoms belong to one silica, right? Each oxygen atom is being shared by 2 silicon atoms. That means 4 into half will give me 2 oxygens. So that's why we write it as a SiO2, not SiO4. Right, so please keep this in mind. Now, if I try to supply an oxygen, what the oxygen will do, this oxygen will taken away. Let's say I break this chain by supplying oxygen. So then this oxygen will come out. This oxygen will go to this guy. Now if I supply more amount of oxygen, right? So what happens is, whenever chain breakage happens, let's say if I break this guy, so I'm again supplying one oxygen atom to that guy. This guy already has 2 oxygen atoms, 2 effective number of oxygen atoms. Now what I'm trying to do is, I am trying to supply extra 2 oxygen atoms such that to balance this 2 oxygen atoms, right? The extra oxygen atoms. So that's why we write it as SiO4 minus 4. Now everything is like separated. So each silicon atom will get 4 oxygen atoms. but initially it was only each silicon atom is getting 2 oxygen atoms effective. I'm not talking about total. If I'm talking about total, it should be 4. If I'm talking about effective, it is 2. Right, so we already have effective 2 oxygen atoms. When I will supply 2 more extra oxygen atoms, so it doesn't needs to share. It need not to share, right? So it got everything 4 oxygen atoms. It need not to share any extra oxygen atoms with any silicon atom, right? So that's why only 2 moles of calcium oxide is required. Again, effective. So please keep in mind. So only 2 moles of oxygen is required. So that's how this happens. So for every 1 mole of calcium silica, you need to add 2 moles of calcium oxide. And this theory goes same for P2O5, phosphorus pentoxide. So for phosphorus pentoxide is not a simple structure, right? So it's not straightforward. Now, likewise, 3 molecules of your 3 moles of oxygen is required, right? So P2O8. This is -6. This is the type of oxide you will form. Okay. So phosphorus has 5 atoms to share, right? So let's P oxygen, 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 oxygen. Okay. So now 1, 2, 3, 4. Okay, 1, 2, 3, 4, 5, 6, 7. So 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. So yeah, maybe this is how it forms. Because your oxygen needs to be shared, right? So that thing should be kept in mind, right? So P2O5, how many oxygens are there? How many? You have 8, right? So 8 should look like this. Okay. You can involve double bonds also, so there is no need for this thing. Let's say this is my phosphorus atom, this is my phosphorus atom. So my phosphorus pentoxide. Let's not see that 3-dimensional structure. Okay, let's only see if I'm talking about Lewis structure. No, let's move on to the next part because it is quite complex to draw the 3-dimensional structure, you know. Or if I'm talking about just a P2O5, you can represent it as like this. This will be better. One, two, three, four, 5. P2O5. That's it. Okay. So if I try to mention in 3 dimension, it will get messy. Okay. Now this is my P2O5 structure. Now I need to add how many calcium oxide atoms? I need to add 3 atoms. Okay. So in 2 dimensions, see, in normal, if I'm only talking about P2O5, it looks simple. I need to only supply 1 calcium oxide, right? So but that's not the case. So 3-dimensional, it looks more messier. Okay. So yeah, you need to supply at least 3 oxygen atoms. So I can because it will become, I cannot draw it here. I'll get the image in next session. Okay, I can show you the 3-dimensional structure of it. So you need 3 calcium oxide atoms to completely neutralize, and same goes for the aluminum oxide. You need to have 3 number of atoms. Okay. So basicity can be defined as 1 number of moles of basic oxide. Let's say if my slag only contains SiO2 and CaO, then it will be 2 times of number of moles of acidic oxide or number of moles of silica. Okay, if my B is 1, then it is neutral. If my B is less than 1, then again simple, it is acidic. That means this is greater than this guy. If B is greater than 1, that is basic. This guy is greater than this guy. Now if my oxides contain pentoxide and alumina, then what I need to do is, all I need to do is simple. I need to subtract it. Subtract it from where? Because they are being consumed, right? So I need to subtract it from 3 times number of moles of Al2O3 plus number of moles of P2O. That's it. This is about the basicity. Now basicity is very important because it depends upon because it is important. You need to pick up the types of oxides, right? If you have silica, you cannot add silica. Okay? You need to add basic oxides. You cannot add P2O5, right? So if you want to pick up, then you need to add the respective oxides depending upon the type of impurities in there. Now moving on to the oxidizing power of slag. Now what do we mean by oxidizing power of slag? Oxidizing power is nothing but you can even say reducing also. So you can have 2 types of slags. This is very much important in your iron making. Okay, in steel making also this is very much important. You have your oxidizing slags and you have the reducing slags. Now what do you mean oxidizing slags? Oxidizing slags are nothing but they will oxidize your metal atoms or metals or impurities. Okay, and then they will form metal oxide, and this can be picked up. So it's nothing but the transferring of oxygen from slag to metal. So that is oxidizing. If it takes oxygen from metal to slag, that is reducing. Okay, so that's it. And now some of the some oxides in slag cannot supply how should I say supply oxygen to the metallic bath due to their strong bonding with oxygen. Okay, so now supply oxygen to metallic bath. So some slags may not have. Some slags, what they do is they can supply oxygen to your metal bath. So what happens then is let's write an equation instead of getting writing. So this is my equation, Fe plus. So these symbols are very much important in metallurgicals because this symbol represent it is in slag. This symbol the square brackets represents it is in metal pool or liquid metal. It is also in metallic state, but this is in slag state. I mean this is in slag. It is ionic form. Ionic, it will be free ions depending upon the type of slag. You will have free ions. Okay. Now, so if I write this equation, the equilibrium constant will be the activity of FeO divided by activity of Fe times activity of oxygen. Right. So if my oxygen in the metal bath increases, okay, so how so if my oxygen content, so for example if this guys goes down, then what happens? The FeO will get reduced. Right. So for example, if my oxygen content in my slag in my metal increases, then this reaction happens and it will move forward and you will have FeO, right? And this FeO will be picked up by slag. So that's what happening. So you are supplying oxygen and this oxygen can come from slag, then you call it as an oxidizing slag. And if this oxygen is being picked up by your slag by some impurities, then that is called as a reducing slag. Now, FeO in itself is your basic slag, right? So the basicity, what it does is, so your FeO in itself is your basic slag that can react with your acidic impurity, acidic oxides, and it will form silicates. So that is also is possible, right? So now, so in your steel making process, slag can be highly basic and highly oxidizing, right? Or highly basic and highly reducing. So this two can be happen in your steel making. It depends upon your FeO content, right? So if your FeO content is large, then you call it as oxidizing slag. So that means if FeO is less, then you call it as a reducing slag. Okay, and FeO can even react with some of your impurities. So in basic steel making, what happens is, whenever you lance, so you lance with oxygen, right? And because of this, whenever you try to purge some air into your liquid, it will form foam, right? It will form emulsion. You can call it as an emulsion also. So in this emulsion, what happens is, because of this oxygen, there will be carbon. So whenever you are trying to purge oxygen, there are impurities like carbon. It will form carbon monoxide because of the temperature, and that carbon dioxide will also have some. It will go into slag and it will form emulsion. And in slag, you will have FeO, and also you will have carbon monoxide. And this carbon monoxide will again reduce your FeO, and that Fe will trickle down through those bubbles to your melt. Okay, so you can see it now, the slag acting as your reducing slag. So once your emulsion forms, your slag can act as a reducing slag because it is taking oxygen from your iron. Okay, so initially your slag will be your oxidizing slag, and once the impurities, the carbon starts oxidizing, forms carbon monoxide, it will form emulsion, and your slag becomes reducing slag, even though your slag is basic, right? Because you are adding calcium oxide, your basic reduced flux is your calcium oxide, right? You need to take out the silica, whatever is there. So that's how the nature of slag changes from oxidizing to reducing. This is very much important in steel making technology. There is also we need to maintain an eye on clock, because we are an eye on time, because this happens for a respective amounts of time. Initially you have oxidizing slag, and then you have emulsion. Once the whole carbon get depleted, you will not find emulsion, right? Because there is no formation of gases to form emulsion with your slag, right? So yeah, so this is one great property of slag in steel making. Okay, so the next property is sulfide capacity. Sulfide capacity. See, and please remember one thing: you cannot have elemental sulfur in your slag, because elemental sulfur cannot dissociate into ions, right? So that's why you cannot have sulfur, elemental sulfur or metallic. Sorry, not metallic sulfur. Elemental sulfur cannot be dissolved in slag. So that's why we write it like this. You can take it as a sulfur in your metal. React with oxygen, give you oxygen gas, and you have your sulfur. Or you can take sulfur gas. Okay, you can take it this also. So sulfur is only soluble in silicate melts, right? Not sulfur, sulfide. Okay, sulfur is not soluble at all in anything, because it is not ionic. It cannot dissociate into ions, right? So you cannot expect it to get dissolved in your ionic compounds. So sulfide is dissolvable, so that's why you write the equation it like this. Then it will become AS2 to activity, this guy, and if I'm talking about gases, then it will be partial pressure of oxide, partial pressure of sulfur. And here we will have mole fractions coming into picture, activity coefficients also will come into picture. So depending upon the partial pressure of oxygen, partial pressure of sulfur, your slag will define what is the amount of sulfide it can take. Okay. So in most of your metal melts, you will not find a large amount of sulfur. So it will be available in elemental state in your liquid melt, right? So you oxidize with your oxygen, and then it will form sulfur dioxide or sulfur oxide. It depends upon it. And electrical and thermal conductivity, again, I have said before, conductivity is very poor because we are talking about oxides, silicates. They don't have good thermal conductivity, but they do not have good electrical conductivity. And also same goes for thermal conductivity because your electrons are not free, and most of the thermal conduction happens if we talk about the percentage of conduction of heat that happens in your alloys or anything. So there are plasmons, not plasmons, there are phonons. Phonons are nothing but collective oscillation of atoms. Correct oscillation of atoms, the phonon movement is sluggish when compared to your electrons movement, because electrons are tiny, they can move very fast when compared to your phonons. So that's why most of your thermal energy will be carried out by your electrons, not by your phonons. So this phonons is very much important in ceramics, right? Because there you have in ionic compounds, and this is more important in ionic compounds because there you do not have that much free electronic structure, right? So phonon motion is sluggish when compared to the electron motion, so that's why thermal conductivity is low. That's why your slag act as a good thermal barrier. Okay, so these are the different properties of slag. Now again, there are some more things, so we'll just brush up it and not discuss very much, go deep into it. Okay. Now slag, what is the next property that we need to discuss? We need to discuss slag viscosity, right? So let's go with slag viscosity. Viscosity is nothing but resistance to flow. If viscosity is high, resistance to flow is high. That means fluid cannot flow freely. If viscosity is low, so viscosity is directly proportional to nothing but the resistance to flow, resistance of fluid flow. It's better to represent it like this, right? Resistance to fluid flow. So viscosity is high, resistance of fluid flow will be high, so it cannot flow. And viscosity can be measured in poise, which can be represented as eta. Okay, it can be centipoise or unity centipoise, poise or centipoise. So again, the viscosity depends upon slag composition, and the viscosity can be represented as eta equals to A exponential activation energy times activation energy of eta by RT. Same, the temperature increases, the viscosity decreases. So where A is a constant, E is your activation energy for viscous flow of the slag, right? And because it is an exponential term, activation energy will decreases rapidly. Activation follows exponential law with your this guy, so not the viscosity follows the exponential term with room temperature. So if the temperature increases, viscosity decreases. Now that is one way of doing. So what if we want to have maintain low viscosity even at low temperature? What should we do? So again, slag depends upon your ions. So ions, again I am talking about the number of coordination bonds. To break these bonds, you need to again supply some flux. So that is again you can add CaF2, which is the best guy to more effective in reducing the viscosity of basic slags. And what this F minus, so whenever this happens, so you will have Ca plus 2 and 2 F minus. So these fluorine ions, what they do is they break your hexagonal network in your basic slags. Okay, so and if you break the network, then your viscosity will goes down. So that's how at room temperature, not room temperature, okay, at less temperature when compared to your normal viscosity temperatures, you can attain it at lower than that, like maybe less than 200 degrees centigrade. Okay, so 200s, like, so for example, if my viscosity is some x value at 1500 degrees centigrade, the same can be achieved at 1200 degrees centigrade by adding Cl. So that's what it does. Again, alumina. So Al2O3 is your amphoteric. So again, it can act as a basic slag breaker, network breaker in acidic slags. Okay, and you need to make sure that this alumina can act as a network former in basic slags. Okay, so that thing needs to be taken care of. So in basic slags, it will increase your viscosity. Okay, so yeah. So in acidic slags, it will freely give you 2 oxygen atoms. Right, 2 oxygen ions. Right. Okay, so this is not. Now that is about the viscosity. There are different diagrams for there are slag viscosity diagrams also. So that can be easily understood because it's not very hard to understand. So you have your effect of temperature. So when temperature, it's straightforward. When you increase the temperature, viscosity goes down. But if you add some basic fluxes, so that thing also will further reduce your viscosity. So yeah, in slags you can have different types of oxygen. One is totally bonded, that can be in form of silicates, okay, or one as your free oxygen ion that readily separated from calcium plus, free, and the oxygen atoms that are that have bonded with your silicon, okay, or the bridge breaking oxygen atom, that you can call it as that also. So bridge break, or you can call it as a non-bridging. So one is the bridging, which is present in this guy. This is your free oxygen. So yeah, so this is about that. Now moving on to the slag theories. Now how do you know what is the composition, what is the activities? So to do that, see, whenever we are talking about activities is nothing but activity of any component I will be given as activity coefficient of I times mole fraction of I. So this is your non-ideal case. If I am talking about ideal case, the activity coefficient will be 1. It will directly proportional to mole fraction. This is where Raoult's law comes. Okay, this is for ideal cases, which is not good assumption for many of the cases. If my micro constants are so low, I mean the concentration is so less, that you can fix this activity coefficient. See, this activity coefficient also depends upon their composition. Please bear that in mind. It also depends upon chemical potential also. So it depends upon your composition, which in turn depends upon your chemical potential. Right? So there are many things that will come into picture. So what does Henry law takes? Henry law deals with whenever you have very minor amount of constituents, you can fix this activity coefficient instead of changing with composition. Okay, so that is about Henry law, right? So, and this activity coefficient depends upon the interaction between your cations and also the interaction between your anions. Now there are many models. Okay, so one of the model is Temkin model. So in Temkin model, what does it say is, and again, you should also involve the configuration entropy. So that's why we should also have one assumption called random mixing. That means let's say if you find calcium here, then the probability of finding the oxygen atom will be half. Any other anion will be half. Okay. Number of anions divided by total number of that anion divided by total number of anions. Okay. So that's about that. And the next important thing is cations and cations will not interact, anions and anions will not interact. So that is also the next assumption. No interaction between same type species, same charge type species, right? No interaction between same charge type species. That is also another assumption. Apart from this assumption, there is also another assumption in the Temkin model. What he say is the slag will have complete dissociation of ions. That means you will find cations and anions separately. Okay, so yeah, and this assumption also comes here. There is no interaction between the same charge, and also there is a full random mixing. Okay, then I can directly write, if suppose I have activity of silica, this can be written as activity of Si+4 and activity of oxygen -2. This is what Temkin model says. Okay, so now there are two types of theories: the ionic theory and molecular theory. So we will again, this Temkin theory is also ionic theory, and there is also another theory called a Flirt's model. And Flirt's model further simplifies that the activity of elements in liquid melt is 1. What do I mean, right? Let's say I have sulfur, let's say I have oxygen in slag, and this sulfur will be picked up by my slag, and oxygen will be thrown into my melt. Let's say this is my reaction. Now, what the assumption is, let's say if I write to equilibrium constant for this reaction, then this will be my activity of this guy times activity of oxygen divided by activity of oxygen. And the other thing is activity of this guy divided by activity of sulfur. Right? You can write both. Now, next is there is another theory called Mason theory. This will be 1, this will be 1. So directly we are dealing with these two guys. The activities of sulfur and activities of oxygen in slag. So we are only concerned about slag activities, elements of activities in slag. There is another theory called Mason theory. Now here we have discussed that there is a complete dissociation of slag. That means there is no interlinking or bridging between your compounds. But Mason theory involves the bridging. Okay, so that means you still have some bridging, not complete dissociation. There is some dissociation, breakage of chains, but you still have some bridging. So if I am talking about silica, then according to Mason theory, I will have complete dissociated part also, and a bit dissociated, and same, and also SiN over 3n plus 1 and 2 of n plus 1. Okay, so this is your empirical formula. So these are different types of silicates that you can find in your slag. And please remember, this we are talking about in equilibrium states. So that thing needs to be kept in mind. Okay. We are talking about equilibrium states. Now, so maybe should I write all the silicate reactions? Right? It's not like that much useful, you know. I can directly write the silicates, right? So in Mason theory, what does it say is whatever the whenever I have silicates, let's say I will just write two reactions. Okay, so I have Si2 plus 7 minus 6 plus 1 oxygen ion is released. So my K1 will be something divided by products divided by reactants, and the same goes for Si3O8, Si3O10 minus 8 plus if some other silica gets attached, then I have Si4O13 minus 10 plus O minus 2, and then here again I have some K3 equilibrium constant. From Mason theory, the main assumption is all these, there will be other, if I keep on adding silica, I will have more number of equilibrium constants coming, right? So these all are equal to one value K. That means they are all equal. That means every reaction, right, every K value can be represented in terms of this guy, right? Why? Because every time we are trying to involve silica, and whatever the product is again acting as a reactant for the next reaction. Right. So I can generate an empirical formula. Right. So let's write the number of silicate anions. If I want to write the number of silicate anions, then I need to know. If I need to know the summation of silicate anions, then I need to know the number of moles of this guy, then I need to mole fraction of Si2O7 minus 6, the total mole fraction of silicate ions, and also the mole fraction of Si3O10 minus 8. So this reaction, it will go on continue. So finally I will remain with SiO4 minus 4 divided by 1 minus K mole fraction of SiO4 minus 4 divided by mole fraction of minus 2. It is very much useful, you know, and this is equals to 1 minus mole fraction of O minus 2. Okay. So you can equate it and finally get a relation. Now that's how you find the mole fraction of silica. Okay, and mole fraction of silica can be easily written as SiO2 will be written as number of moles of silica divided by number of moles of silica, number of moles of metal oxide, number of moles of silicates in free form, in oxide silicates form. Right. So number of moles of SiO2 directly can be told from what is the silica, different types of silicates, right? And same comes here also. See, now let me explain clearly. Whenever I have 1 mole of this guy, that means I have 2 moles of silica. 2 moles of silicon, I can take it. Right. So same goes for if I have Si3, then I will have 3 moles. Now the thing is, see, you will write all these things here also. Okay. Now whenever you have a free metal oxide, you should also need to add 1 mole extra. Right. So you have you also have O minus 2 also, right? You also need to add extra number of moles because of this oxide. That's why you will add 1 mole extra from this guy, from this guy. So that's why this number will become 3 down. That's how the equation we got. Okay, so for every silica SiO4 minus 2, SiO4 minus 4, you need to add how many moles of metal oxide? 2 moles. So that's why this will become 3. You already have 1 mole. You are equating the silica to your number of moles of oxide, free oxide that is being present or that is being added. Right. So that's why it becomes 3 moles. And if you have this 2, again you need to add extra 2 moles, that will become 5. Okay. So that's how you need to add 2 moles for each of them. Okay. Now, and finally you will get if you use this guy from here, you will have final relation. So that's straightforward. I'm not going to derive it again. Again, it will also take much time. We can do this derivation in extra sessions. Okay? There is also this molecular theory of slags where we directly we say that they directly form different types of silicates, and we directly count the number of moles. Okay, so we will not take much into it. Right. So this is about these guys. Okay, so yeah. This is about slag, and see, I have already mentioned. See, we have discussed matter smelting in brief, right? Why do we do partial roasting? Why do we do matter smelting in the beginning of slide? So I will not discuss it again. Okay, so that's all for the today's session, not the whole session. Okay? I mean the lectures, right? The 5 lectures. These are the things that they have covered. Now let's move on to the problem solving. Okay. And roasting is a pyrometallurgical process. Please remember that. Roasting, smelting, they all come under your pyrometallurgical process. Okay, so roasting is primarily done in the ores for chalcopyrites. So you do the partial roasting, you convert them into oxides, and then so you have some sulfides, right? So you have some sulfides, you do the roasting, you convert into oxides, and then you add some flux, you get the slag. So this whole is your pyrometallurgical process. This is your roasting, and here you have smelting. Okay. Now the next question. Okay. So this is about the roasting. Okay. Now what happens? What is dead roasting? Again, I will mention dead roasting is nothing but, suppose you have any type of sulfide, you give enough amount of oxygen such that it will form the most stable oxide that it can form. Okay. So how many moles should I separate? I need to give 3/2 moles of oxygen. Right. Yeah. This is dead roasting, and sulfation is nothing but you are forming a sulfate. Remember. So whenever you have metal oxide that reacts with sulfuric acid plus oxide, not sulfur oxide plus oxide, that will give you sulfate. Okay. So this is one reaction. Chloridizing roasting, what you are doing is you are trying to form chlorides. So yeah. Again, reduction with hydrogen of sulfide ores is not suitable. It is not good. Okay, it is thermodynamically difficult also. You need to attain very high temperatures and good conditions. and noble sulfides are almost stable, right? Just like platinum sulfide, it is very much stable, right? And one peculiar property of lead sulfide is lead sulfide can be reduced with hydrogen, but the temperature is such that it will become volatile, so you cannot do reduction there also, right? Even though the temperature is less, but the reduction, the lead sulfide will instantaneously become volatile at that temperature. Okay, now what happens in flash smelting? Flash smelting, again the same happens. So you do the partial roasting there also. You have CuFeS2, you oxidize it at a minimum amount of oxygen, which it will form copper sulfide, FeO, SO2. So, and there will be some amount of FeS also, which can be remined if you are not supplying full amount of, if you are not doing the dead roasting. And this is an exothermic process, so this heat also will melt your this guy, so you will have your copper sulfide plus FeS and FeO plus SiO2 as slags. This is slag, this is melting. So finally we will end up with smelting. So everything, so both of things happens in a single step, flash smelting, right? And there is dead roasting. Dead roasting is nothing but you convert everything into oxide, right? So I've said before. Now there are some simple questions, right? I hope I need not to tell them. So for example, A reacts with oxygen and it will form AO2, and this is my delta H. Delta H, the enthalpy, is represented in per mole. Please remember that. It is remember joules per mole. So it is for per mole. That means 1 mole will give you 1 mole of A will undergo roasting and will give delta H1 amount of joules. Okay. So if I have 0.5 moles, then it is simple. It's just delta H1 divided by 2. Right. So yeah. So I will not discuss these problems. Okay, these are simple one. And also please remember, if I am talking about 3 component system, that means my components are 3. If I am fixing my temperature and pressure, then the 2 will go away. So F equals to C minus 3 plus 2. So if I am my pressure and temperature are constant, then 2 will go out. Okay. Or if you take only pressure as a constant, then I will only remain with temperature. Okay. Or if I constant the temperature and remain with pressure, right? My components are 3, then 4 minus P. So if I am talking about 4 phases, right? So if my reaction involves 4 phases, let's say this is 1 phase, this is 2nd phase, this is 3rd phase, this is 4th phase, then the number of degrees of freedom will be 0, right? So why is that? Because when I am fixing my oxygen and sulfur dioxide, the ratios, then my number of degrees of freedom will be 0, right? And maximum number of maximum number of degrees of freedom that you can get if I have 4 components, right? If my components are 4, and if I fix my temperature and pressure, then the F will be directly will be 4. So now if I have a single phase region in my predominance area diagram, so if this is, let's say if this is my region, This is my whole region. Okay, so on this region I can change PO2 and PSO2, both can be changed, and I can lie at any point, right, in this diagram. What about the equilibrium line? So at the equilibrium line I can only move, suppose if I have two phases, this is at MO2, MS2, I have 1 degree of freedom, right? If I increase something, I can lie on this guy, or if I decrease something, I can lie on this guy. And at this point, this univariant point, I cannot move, right? I cannot change anything. Even if I change your pressure, temperature, no, it will not change. That's what happens in the water, right? So degrees of freedom will be equals to number of components, right? What is it? What's the relation? Yeah, number of components minus number of phases. Okay. So if my components are 2, why? Because it is hydrogen and oxygen. And if I'm talking about phase diagram, not the elemental phase diagram, okay? If I'm not talking about H2 and O2, if I'm talking about H2 as itself, then the component will be 1. Why? Because water is a singular, right? So then what happens is the component will be 1 minus number of phases. Water has how many phases? 3. Solid, liquid, vapor. So 3 plus 2. So number of degrees of freedom will be 0. So that's why you will have a critical point for a water where your solid, liquid, gas will what should I say? Solid, this is solid, liquid, gas. They will form an equilibrium point. Okay. So if you move from that equilibrium, you can end up in any of these phases. So that's what invariant point is. Even if you change anything, you can change pressure, temperature, it will not, the invariant point will not change. So that's why that name came from the invariance. Okay. So yeah, that's all for today's session. Okay. So if you have any doubts, you can stay or you can leave. Let me stop the recording.